Hello and welcome to MaxSurf Webinar 6 of Video 1 on probabilistic damage stability. This video introduces us to the basic concepts. Let's start with some terminology. Traditional damage stability is called deterministic damage stability. In this type of analysis, we prescribe a rule to determine whether the vessel will survive based on a prescribed damage event. For example, the rule might specify a certain length of damage along the hull, and the criteria might be that the margin line should not be immersed or something like that. The probabilistic approach is a bit different. What we do there is we estimate a total probability of survival from the contributing probabilities of a whole range of damage events. So we basically look at a whole range of damage conditions, estimate the probability of each one, and then combine them all together to get a total probability of survival. A little bit of history is in order. The probabilistic approach started way back in 1973, and the first implementation was just an alternative method for computing stability of passenger ships. In 1990 that was upgraded, and a new mandatory approach for cargo ships and ro-ros was developed, and these two methods were slightly different. There was a research project called the HARDA project in Europe, and the result of that was a harmonization of those two rules into Marine Safety Committee Resolution 21682. It brought those two together and made them applicable to both passenger and cargo ships. There have been some other MSC documents since which update the rules slightly and provide explanatory notes and also include and exclude certain types of vessels. The basic approach to the calculation of probabilistic damage stability is that we assume that damage has occurred in a certain location in the vessel, and we calculate the probability of that damage occurring based on its location and its extent or length, and that probability is P. Given that particular damage, we then calculate a probability that the vessel can survive, and that probability is S. So that means that the probability that the vessel can survive that particular damage is P times S. If we look at a number of different damage scenarios, we can then sum them all together. And so we sum a combination of the probabilities of damage and the probabilities of survival. We add all those together and we get a total probability of survival. This is called the attained subdivision index and is commonly labeled as A. We compare this to a required subdivision index R. R is computed in the code from a formula based on the length of the vessel, and for passenger vessels the number of passengers on board. So for our vessel to comply, the requirement is that our attained index A must be greater than our required index R. The logic of this probabilistic approach is that two vessels with the same attained index A are considered to be equally safe. The data that's used to calculate the probabilities of damage and survival is based on statistics that have been collected from actual casualties. The workflow that we use in MaxSurf for carrying out probabilistic damage stability is that we first define the hull form in MaxSurf as usual, and we define the compartmentation in Hydromax as usual, the location of our tanks and compartments. We then set up some subdivision within the vessel, and that subdivision defines a number of zones, and we damage each zone in turn. For each damage condition, we carry out a large angle stability and we compute the vessel's GZ curve, and from the properties of that GZ curve we calculate the probability of survival S. We sum those together. It's done in Hydromax Ultimate. The combination of all of the probabilities of those damage conditions will give us our attained index A. If it exceeds the required R, then we're okay. If A is less than R, then we may need to modify our compartmentation in order to comply with the code. That completes our introduction to the probabilistic damage approach. Thank you for watching.